February 19th, 1942. The Pentagon, Washington, District of Columbia. Major General Eugene Raybould, Chief of the United States Army Corps of Engineers, held a classified British technical manual in his hands. The document described a bridge system so simple it seemed almost childish rectangular steel panels that locked together with pins, assembled by hand, requiring no cranes, no special tools, no engineering expertise beyond basic training. His staff had spent 3 days analyzing the specifications. Every calculation said it shouldn't work. Steel panels weighing 570 pounds each, carried by 6 men, somehow strong enough to support a 40-ton Churchill tank. The physics seemed impossible. The British claimed they could build a 120-foot span in 8 hours with 40 untrained soldiers. "It's too simple," Colonel Harold Barnes stated, tossing his analysis across the conference table. "Our Hutton and H-20 bridges are engineered properly. This Bailey system, it's like building bridges with an erector set." If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. General Raybould studied the photographs. British engineers in North Africa, assembling these bridges under fire. Tanks crossing rivers that should have stopped entire divisions. The bridges looked crude, utilitarian, nothing like proper American engineering, but they worked. Outside the Pentagon windows, America was 4 months into a war it wasn't prepared to fight. Tank production had finally reached meaningful numbers. The M3 Lee, the M4 Sherman, both weighing over 30 tons. Every planning scenario showed the same problem. Rivers, dozens of them, hundreds, across France, across Germany. And America's existing bridge systems were designed for a different war. The crisis had revealed itself during war games at Fort Benning in January 1942. The 34th Infantry Division needed to cross the Chattahoochee River. Engineers assembled an Otten bridge, the Army's standard fixed bridge for medium loads. Construction required 16 hours, dozens of trucks hauling components, a specialized crane, and an engineering company with extensive training. Lieutenant Colonel David Parker filed his report with brutal honesty. In combat conditions, with enemy fire, this timeline becomes impossible. We cannot afford 16 hours at every river crossing. Modern armoured warfare moves faster than our bridge-building capability. The floating bridge alternatives presented their own disasters. During Tennessee manoeuvres in August 1941, 7 soldiers died when pontoon bridges collapsed under M3 tanks. The weight distribution was wrong, the balance calculations imperfect. Each accident delayed operations by hours, sometimes days. Captain Robert Morrison, who witnessed one of the collapses, described it in his after-action report. The tank reached mid-span when the pontoons began to tilt. The driver tried to reverse, but the weight shifted too fast. The tank rolled sideways into the Cumberland River. 3 men drowned before we could get them out. We spent 2 days recovering the vehicle. The British Bailey Bridge manual sat on Raybould's desk like an accusation. While American engineers built monuments, the British built tools. While American doctrine demanded perfection, British pragmatism settled for adequate, fast, and repeatable. The specifications were almost insulting in their simplicity. Each panel, 10 feet long, 5 feet high. Standard steel angles available from any supplier. Simple welding, nothing exotic. Pin connections that required only sledgehammers. No precision alignment, no special training. A child could understand the assembly sequence, but the genius was in mathematics. 2 panels side by side created a bridge not twice as strong, but 2 1/4 times as strong. Stack them vertically, and the strength increased exponentially while weight increased linearly. The load distribution through triangulated trusses transformed simple components into engineering that worked. Colonel Thomas Casey, the Army's chief bridging officer, had visited the British experimental bridging establishment at Christchurch in December 1941. His confidential report reached Raybould's desk in January. The Bailey Bridge represents a revolutionary approach to military engineering. It sacrifices aesthetic elegance for functional simplicity. It democratizes bridge construction, removing the need for specialized expertise. Most importantly, it works under combat conditions where our systems fail. The decision point came during a Joint Chiefs meeting on February 21, 1942. Admiral Ernest King argued for immediate adoption. "Gentlemen, we're planning amphibious operations across the Pacific and Atlantic. Every invasion requires bridge building under fire. The Bailey system lets ordinary infantry engineers do what currently requires specialist companies. We license this design, or we slow every offensive we plan to conduct." General George Marshall added weight to the argument. "The British are building these bridges faster than the Germans can destroy them. That's the war in a nutshell. We must match their capability or accept that rivers will stop our advance while the enemy reorganizes." Raybould made the call that afternoon. License the Bailey Bridge. Begin American production immediately. Adapt it to U.S. Army specifications. Call it something American, the portable panel bridge. But get it into production before summer. The licensing agreement was signed on March 3, 1942. The British government requested no royalty fees. Donald Bailey's design would be freely shared among allies. All Britain asked was that America maintain the precise specifications to ensure interchangeability. A panel made in Detroit must work with panels made in Birmingham, England. The Corps of Engineers moved with unusual speed. On March 15th, contracts were awarded to 3 American firms. Detroit Steel Products Company received the primary contract. The American Elevator Company and Commercial Shearing and Stamping Company received secondary orders. Each firm was given the same mandate: begin production within 90 days, reach full capacity within 6 months. What happened next revealed both the strength and weakness of American industrial capacity. Detroit Steel Products assigned their best engineers to the project. James Whitmore, their chief design engineer, read the Bailey specifications and immediately began making improvements. His modifications report, dated April 2nd, proposed 17 changes to the original design: stronger welds, reinforced corner connections, precision-machined pinholes for better fit, upgraded steel alloys for increased strength. Each modification made engineering sense. Each one violated the fundamental principle of the Bailey Bridge simplicity that enabled mass production and universal interchangeability. Colonel Parker, assigned as the Army's liaison to Detroit Steel, rejected every modification. His memo, preserved in the National Archives, stated, "The Bailey Bridge succeeds because it demands nothing special. Your improvements require special welding, precision machining, and upgraded materials. This defeats the purpose. Build it exactly as specified, or we'll find someone who will." The tension between American perfectionism and British pragmatism would define the entire production effort. American engineers struggled to accept that adequate was better than perfect when adequate could be produced in vast quantities quickly. Production began in June 1942. Detroit Steel's first panels rolled off the line on June 8th. The initial inspection revealed a problem. The panels were beautiful. Welds were perfect. Finish was immaculate. But they cost 3 times the British price and took twice as long to manufacture. Whitmore defended his work. "We're building to American standards. These panels will last decades. The British panels are barely adequate for temporary military use." Parker's response was immediate. "We need 10,000 panels in 6 months for the North Africa invasion. You're delivering quality that will survive 50 years when we need quantity that must survive 50 days. Simplify your process or lose the contract." The fundamental difference in approach was this: British production dispersed among 650 firms, each making specific components under rigid specifications. American production concentrated in a few large facilities, each building complete bridge kits. The British method ensured perfect interchangeability. The American method promised efficiency but risked compatibility problems. By September 1942, 3 American manufacturers were producing Bailey bridges, now officially designated the M2 Portable Panel Bridge. Monthly production reached 1,000 panels. The target was 5,000 panels per month. America was building bridges, but not nearly fast enough. The first American-built Bailey Bridge entered service in October 1942 at Fort Bragg, North Carolina. The 292nd Engineer Combat Battalion assembled a 100-foot span in 7 hours. The demonstration succeeded, but problems emerged immediately. Panels from Detroit steel fit together perfectly. Panels from American Elevator fit together adequately. But mixing panels from different manufacturers created gaps, misalignments, tolerance issues. Captain Harold Stevens documented the problem. Pinholes on Detroit steel panels measure exactly 0.875 inches. Pins measure 0.870 inches. Perfect fit with 0.5 thousandths clearance. American. Elevator pinholes measure 0.880 inches. The same pins fit loosely. British specifications allow tolerance of plus or minus 0.005 inches. American manufacturers each interpreted this differently. The tolerance crisis threatened the entire program. If American-made panels couldn't reliably interchange with each other or with British-made panels, the system's fundamental advantage disappeared. Major William Henderson, assigned to solve the problem, visited all 3 manufacturing plants in November 1942. His report identified the core issue. American firms are accustomed to achieving high precision through careful manufacturing. British firms achieve consistency through rigid quality control gauges. The British method works better for this application. Henderson's solution was bureaucratic but effective. The Army Corps of Engineers would provide master gauges to all manufacturers. Every panel, before shipment, would be tested against these gauges. Any component failing the gauge test would be rejected and scrapped, regardless of its absolute quality. Detroit Steel protested. "You're asking us to reject panels that are perfectly good because they're too precise. That's insane." Henderson's response defined the difference between engineering philosophy and engineering pragmatism. "I'm asking you to reject panels that don't match the system standard. A panel that's perfect in isolation but incompatible with the system is worthless. A panel that's barely adequate but universally compatible is valuable. Build to the standard, not to your standard." By January 1943, American production had reached 2,000 panels per month. The gauge system was working. Interchangeability improved. But America still lagged Britain, where production exceeded 15,000 panels per month across hundreds of small firms. The production challenge intensified with the North Africa invasion. Operation Torch-In, November 1942, required immediate bridge deployment. The 237th Royal Engineers Field Company built the first operational Bailey Bridge at Mejez El Bab in Tunisia on November 26. American forces watched with mixed admiration and envy. Lieutenant Robert Shaw, observing the construction, wrote in his diary, "The British made it look effortless. 40 men, no officers supervising. They assembled panels like stacking building blocks. No hesitation, no measurement, just practiced rhythm. The bridge was complete in 9 hours. Our engineers are asking for the panels and training." American-built bridges reached North Africa in January 1943. The 509th Engineer Light Ponton Company received the first shipment, 100 panels, enough for multiple bridges, manufactured by Detroit Steel. Captain Edward Morrison supervised the first American Bailey Bridge construction under the Portable Panel Bridge designation. Medjugorje River, February 8, 1943. Morrison's engineers had trained for 2 weeks on the Bailey system. The British liaison officer, Major Kenneth Ray, watched skeptically. Americans built things bigger, stronger, more complicated. Could they accept simplicity? The assembly began at dawn. 6-man teams carried panels from trucks to the assembly site. No cranes, no heavy equipment. Just men with panels, working in sequence. Panel 1, drive pins, secure. Panel 2, connect, drive pins. The rhythm established itself naturally. Morrison watched his men work with growing confidence. This wasn't engineering in the traditional sense. This was manufacturing, repeatable, trainable, scalable. Any soldier with basic competence could learn this in days, not months. The bridge extended across the Medjerda, 60 feet, 80 feet, 100 feet. At 120 feet, the far bank reached. The span was complete. Total time, 8 hours, 30 minutes. Close enough to British standard to prove the concept worked for American forces. Major Ray approached Morrison. "Well done, Captain. Your men learned quickly," Morrison replied. "The system teaches itself. That's the beauty. You can't assemble it wrong without it being obviously wrong. It's almost foolproof." Testing began that afternoon. An M4 Sherman, 33 tons combat loaded, rolled onto the bridge. The span deflected 2 feet at mid-span. The sound of straining steel echoed across the river. But it held. The Sherman crossed, followed by 17 more tanks, then trucks, then artillery. The bridge carried the entire 2nd Armoured Division across the Medjerda in 2 days. But problems emerged as American forces built more bridges. In March 1943, the 31st Engineer Combat Battalion discovered that several panels wouldn't connect properly. The pinholes were either slightly too large or too small. Investigation traced the problem to commercial shearing and stamping. Companies' fabrication gauges. The gauges, which should have been calibrated monthly, hadn't been checked in 6 months. Wear and poor maintenance had ruined their accuracy. Panels manufactured to these incorrect gauges were dimensionally wrong. Not obviously wrong, just wrong enough to cause problems when mixed with correctly manufactured panels. The Corps of Engineers audit in April 1943 revealed the scope of the disaster. 850 Bailey bridge kits, totaling approximately 17,000 panels, had been manufactured to incorrect dimensions. These panels couldn't be repaired. They couldn't be modified. They could only be marked as standalone bridge sets, never to be mixed with standard panels. Major Henderson filed his report with barely controlled fury. "Commercial shearing lost us 850 bridges through negligence. That's enough bridging to cross every river from Tunisia to Rome. We cannot afford this level of incompetence when men's lives depend on our equipment." If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. The gauge crisis forced a complete overhaul of American Bailey Bridge production. New inspection protocols, mandatory monthly gauge calibration, Army inspectors at every factory, spot checks on random panels from every batch. The bureaucracy increased, but so did reliability. By May 1943, American production reached 4,000 panels per month. Quality was consistent. Interchangeability with British panels was verified. The United States Army had successfully industrialized the Bailey Bridge, though not without painful lessons in the difference between building things well and building things correctly. The lessons learned in North Africa transformed American bridge production. By June 1943, as Allied forces prepared for the Sicily invasion, the United States had become the world's 2nd largest producer of Bailey bridges. But production numbers told only part of the story. The real test would come when American combat engineers faced the same conditions that had made the Bailey Bridge indispensable to British forces. Rivers destroyed by retreating enemies, bridges needed immediately, construction under fire. Sicily, July 10, 1943. The invasion of Operation Husky required bridge building on an unprecedented scale. German forces, retreating north toward Messina, destroyed every bridge in their path. The strategy was simple: slow the Allied advance, buy time for organized withdrawal, turn every river into a defensive position. The 120th Engineer Combat Battalion landed on the 2nd day of the invasion. Captain James Bradford commanded Company A, responsible for bridging operations in the American sector. His unit carried enough Bailey panels for 6 complete bridges, transported on 40 trucks, each loaded with components that 6 men could lift. The first river was the Simeto, 20 miles inland from the landing beaches. German engineers had demolished both road bridges, leaving only shattered stone piers jutting from the water. The ford was mined. The current was strong enough to make pontoon bridging risky. A Bailey bridge was the only practical solution. Bradford's after-action report, preserved in the National Archives, describes the operation with clinical precision. July 13th, 0500 hours. Reconnaissance complete. Bridge requirement, 140 feet, double single configuration. German observation posts on the north bank. Intermittent artillery fire. The assembly site selected 300 yards from the river behind the ridgeline for cover. The technique developed by British engineers in Tunisia became standard for American forces. Assemble the bridge completely on the south bank, out of sight behind terrain cover. Use rollers to launch it across the red gap, pushing it out like a giant steel ruler until the far end reaches the opposite bank. Private First Class Thomas Chen, a welder from San Francisco, described the experience in a letter home that somehow survived censorship. We worked through the night putting those panels together. You could hear German artillery hitting positions upstream, see the flashes lighting up the sky. But we just kept working, panel after panel. The rhythm got into your bones. Lift, position, pin, move. Lift, position, pin, move. By dawn we had a bridge, lying on rollers, ready to push across. The launch began at 0600, 80 men on push bars, sliding the bridge forward on greased rollers. The cantilever extended over the river, the launching nose angled upward to compensate for the inevitable droop. At 60 feet out, German observers spotted the operation. Artillery shells began landing near the launch site. Corporal William Davies, operating one of the push bars, recalled the moment in an oral history interview in 1998. The first shell hit 50 yards away. We kept pushing. Second shell closer, maybe 30 yards. The captain never said stop. We kept pushing. You get into this mindset where the job matters more than the fear. The bridge had to reach the other side. That's all that mattered. At 110 feet, the launching nose touched the far bank. Engineers sprinted across under fire to secure the bridge and remove the launching nose. The span was complete. Total construction time, including the overnight assembly, 11 hours. The entire 3rd Infantry Division crossed the Simeto that day and the next. 3,000 vehicles, tanks, trucks, artillery, ambulances. The bridge never stopped carrying traffic. Captain Bradford wrote in his summary, "The Bailey system succeeded where traditional bridging would have failed. We built under fire, with ordinary soldiers, using no equipment beyond trucks and manpower. The bridge absorbed several near-miss artillery strikes and continued functioning. This is not engineering, this is industrial warfare applied to bridging." The Italian campaign from September 1943 to May 1945 became the proving ground for American Bailey Bridge operations. German forces adopted a scorched earth policy, destroying infrastructure systematically. By the end of the Italian campaign, Allied engineers had built over 3,000 Bailey bridges in Sicily and Italy alone. American forces built approximately 40% of these, learning and refining techniques with each construction. The Volturno River crossing in October 1943 demonstrated the evolution of American bridge-building capability. The 1139th Engineer Combat Group, commanded by Colonel John Niles, needed to span multiple crossing sites simultaneously. Traditional doctrine said build one bridge, wait for completion, move to the next site. The Bailey system enabled parallel construction. Colonel Niles deployed his battalions to 7 different crossing points along a 20-mile front. Each battalion carried enough panels for multiple bridges. Within 48 hours, 16 Bailey bridges were operational. The speed of the operation shocked German commanders, who calculated that securing such a river line should delay the Allies for weeks. General Heinrich von Vietinghoff, commanding German forces in Italy, stated in his post-war interrogation, "We destroyed the Volturno bridges thoroughly." Proper military engineering doctrine suggested 2 weeks minimum for the Americans to restore crossing capability. They had bridges operational in 2 days. This was not engineering as we understood it. This was industrial production applied to warfare. The psychological impact on German forces was profound. Destroying bridges, mining fords, demolishing infrastructure, none of it bought significant time. The Bailey Bridge had effectively neutralized rivers as defensive obstacles. Geography, which had shaped warfare since ancient times, suddenly mattered less than logistics and industrial capacity. Lieutenant Colonel Charles Jarrett Kerr, the British engineer who had helped develop the Bailey Bridge, visited American forces in Italy in January 1944. He observed the 343rd Engineer General Service Regiment, building a bridge near Cassino under German artillery fire. His report back to the War Office expressed surprise at American modifications to British techniques. The Americans have added efficiency innovations we never considered. They pre-assemble bridge sections on trucks, reducing on-site construction time. They've developed standardized launching equipment that travels with each battalion. They've created floating Bailey bridges using pontoons as supports, extending the span capability beyond our original specifications. Most importantly, they've treated bridge building as a production process rather than an engineering challenge. American production capacity reached its peak in 1944. 25,000 panels per month rolled off assembly lines across the United States. Detroit Steel Products, having overcome its initial resistance to building adequate rather than perfect bridges, became the largest single manufacturer. But the company also learned the lesson that quality control gauges mattered more than absolute precision. The gauge controversy of 1943 taught American manufacturers an important principle. In modular systems, consistency mattered more than individual component quality. A panel that was precisely manufactured to the wrong standard was worse than a panel that was adequately manufactured to the correct standard. By D-Day, June 6, 1944, American forces had accumulated vast stockpiles of Bailey Bridge components across southern England. The 43rd, 44th, and 45th Engineer Combat Battalions, assigned to support the Normandy invasion, carried enough panels to build 50 miles of bridging. The planning assumption was simple. The Germans would destroy every bridge in France. The Allies would rebuild them faster than the Germans could react. The first American Bailey Bridge in Normandy was completed on June 8 near Carrington. The 238th Engineer Combat Battalion built an 80-foot span across the Douve River in 9 hours, while under sporadic German sniper fire. By the end of June, American engineers had constructed over 100 Bailey bridges in the Normandy sector alone. Staff Sergeant Robert Morrison, who had witnessed pontoon bridge failures during Tennessee maneuvers in 1941, found himself building Bailey bridges across Normandy in June 1944. His perspective had changed completely. 3 years earlier, I watched soldiers die when pontoon bridges collapsed under tanks. In Normandy, we were building bridges that tanks crossed without hesitation. The Bailey system removed doubt. You built it correctly or you didn't, there was no ambiguity. The breakout from Normandy in late July 1944 tested American bridging capability on a massive scale. General George Patton's Third Army, activated on August 1st, moved faster than any army in modern warfare. The speed of advance depended entirely on combat engineers, building bridges as fast as armoured divisions could reach rivers. The 88th Engineer Heavy Ponton Battalion, commanded by Lieutenant Colonel Charles Hare, made 15 river crossings as Third Army raced across France. Hare's battalion built 3 crossings of the Seine, 5 of the Moselle, 3 of the Maine. The speed was unprecedented. Traditional military doctrine suggested weeks per major river crossing. Hare's battalion built bridges in hours. Captain Edmund McNeill, serving with the 284th Engineer Combat Battalion, described the reality of combat bridge building in an interview decades later. People imagine it's this smooth operation. You're building the bridge, and German planes drop bombs, machine gun you, shell you with artillery. We lost men. The guy next to you dies. You step over him and keep driving pins. You have to. The tanks are waiting. The infantry is waiting. The bridge has to be built. The Rhine crossings in March 1945 represented the culmination of American Bailey Bridge expertise. Operation Plunder, the largest river crossing operation in history, required bridges across the Rhine at multiple points simultaneously. American forces built 23 Bailey bridges across the Rhine and its tributaries in the first week of operations. The 291st Engineer Combat Battalion built Blackfriars Bridge at Wesel, 1,814 feet, including approaches, the longest Bailey Bridge ever constructed to that date. Canadian engineers led the construction, but American-manufactured panels comprised 60% of the components. The mixing of British, Canadian, and American panels in a single bridge demonstrated that the interchangeability problem had been solved. Lieutenant Scott Babcock, serving with the 617th Engineer Company, witnessed General Dwight Eisenhower cross a Bailey Bridge over the Rhine on March 26, 1945. Eisenhower stopped at midspan, looked at the steel panels beneath his feet, and turned to his chief engineer. "This bridge is the reason we're in Germany months ahead of schedule. The Germans couldn't stop us because we could cross rivers faster than they could destroy crossings." The statistics of American Bailey Bridge production tell a story of industrial transformation. From zero production in early 1942 to 25,000 panels per month by 1944. Total American production, over 200,000 tons of Bailey bridging. Enough panels to build bridges totaling more than 40 miles in length. But the numbers don't capture the human dimension. American engineers learned to build bridges while under fire, in darkness, in weather ranging from Italian heat to German winter. They learned that speed mattered more than perfection, that adequate and immediate beat perfect and delayed. The casualty statistics reveal the cost. Traditional bridge construction under fire resulted in casualty rates approaching 30%. Bailey Bridge construction reduced casualties to less than 5%. The speed of construction, the lack of heavy equipment, the ability to work undercover until the launch phase all contributed to saving lives. Private First Class Anthony Benedetto, later famous as singer Tony Bennett, crossed countless Bailey bridges during the Italian campaign. He wrote in his memoir, "Those bridges appeared like magic. You'd reach a river, expecting to stop for days, and find engineers already, building. By the next morning, tanks were rolling across. The bridges looked temporary, improvised, but they carried the entire war across Europe." American production didn't end with German surrender in May 1945. The Pacific War continued, and Bailey bridges found new applications in jungle warfare. The China-Burma-India theatre saw extensive Bailey Bridge use, with American-manufactured panels shipped across the Pacific for operations in terrain where traditional bridge building was nearly impossible. The longest Bailey Bridge in the Pacific theatre spanned the Chindwin River in Burma, 1,154 feet, built in sections on pontoons during monsoon conditions. American engineers from the 45th Engineer Combat Regiment, working alongside British and Indian forces, completed the bridge in 4 days during torrential rain. The post-war assessment of Bailey Bridge contribution came from multiple sources. General Eisenhower ranked it alongside the radar and the heavy bomber as one of 3 technical developments that shortened the war. Field Marshal Montgomery stated that without the Bailey Bridge, the Allies could not have maintained the speed and tempo of operations necessary for victory. But perhaps the most significant assessment came from German generals during post-war interrogations. General Alfred Jodl, when asked what Allied advantage surprised him most, replied, "Your bridge-building capability. We destroyed bridges confidently, knowing it would delay you for weeks. You built new bridges in days. This undermined our entire defensive strategy. Geography no longer protected us. Your industrial capacity has defeated our military engineering." The irony of American Bailey Bridge production was that it represented a reversal of traditional American engineering philosophy. American doctrine had always emphasized quality, precision, superiority. The best equipment, the best training, the best engineering. The Bailey Bridge taught a different lesson. Sometimes adequate and abundant beats are superior and scarce. Detroit Steel Products, which initially resisted building bridges it considered barely adequate, eventually became the system's greatest advocate. James Whitmore, the engineer who wanted to improve the Bailey design in 1942, wrote a technical paper in 1947, analyzing the system's success. His conclusion: the Bailey Bridge succeeded precisely because it rejected engineering elegance in favor of functional adequacy. It could be mass-produced by hundreds of firms, assembled by minimally trained soldiers, and transported by ordinary trucks. These advantages mattered more than structural sophistication. The cost-effectiveness was extraordinary. A traditional military bridge capable of carrying 40-ton loads cost approximately $50,000 in 1942. A Bailey bridge of equivalent capacity cost $6,000. Production time: 3 days for a traditional bridge versus 8 hours for a Bailey bridge. In warfare, where time equals lives, the Bailey system saved both money and casualties. The standardization enabled by the Bailey Bridge influenced all subsequent American military engineering. The concept of modular, interchangeable components became doctrine, the idea that systems should be designed for ease of manufacturing and field assembly, not engineering elegance, transformed how the military approached equipment development. By war's end, over 700,000 Bailey panels had been manufactured globally. American production exceeded 250,000 panels, roughly 35% of total production. These panels built bridges across every theatre of war, from North Africa to Burma, from Sicily to the Rhine. The human stories behind the statistics reveal the true impact. Corporal William Davies, who pushed that first bridge across the Simeto River under fire in Sicily, survived the war and became a bridge engineer in civilian life. He spent 40 years designing and building bridges and kept a Bailey panel section in his office. That panel represents everything important about engineering, he told colleagues. Not elegance, not sophistication, just the intelligence to solve problems with adequate solutions that can be produced in quantity when needed. Staff Sergeant Robert Morrison, who witnessed pontoon bridge disasters in 1941 and built Bailey bridges across Europe in 1944 and 1945, returned home with a different understanding of engineering excellence. In a speech to engineering students in 1968, he stated, "The best engineering isn't always the most sophisticated. The best engineering solves real problems under real constraints with real resources." The Bailey Bridge was brilliant because it worked everywhere, always, with ordinary people using ordinary tools. Donald Bailey, who sketched the original design on an envelope in 1940, never imagined the scale of American production. When told that American factories were producing 25,000 panels monthly, he reportedly said, "That's more bridge capacity than I dreamed possible." The Americans didn't just adopt the design, they industrialized it beyond anything we envisioned. The final measure of success came from the soldiers who crossed the bridges. Tank crews who drove across Bailey spans stretching over the Rhine, infantry who marched across these temporary structures that carried them toward victory, supply sergeants who watched endless convoys cross bridges that should have taken weeks to build. One anonymous soldier, in a letter home dated April 1945, captured the essence. "We crossed another river today. Engineers built the bridge overnight. Steel panels locked together, strong enough for tanks, built by guys who were mechanics and farmers before the war." That's America. We don't do things the old way. We figure out how to do them fast, simple, and good enough. Then we do them 1,000 times until the job is done. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe. The Bailey Bridge story is ultimately about transformation. It transformed military engineering from a specialized craft to an industrial process. It transformed American manufacturing philosophy from pursuing perfection to embracing adequate solutions at scale. Most importantly, it transformed warfare itself, removing rivers as decisive obstacles and proving that industrial capacity could overcome traditional military advantages. The rejected blueprint, dismissed by British authorities in 1936 as too simple, too crude, lacking proper engineering sophistication, became the foundation for Allied victory. America took that blueprint and did what America does best, produced it in quantities that overwhelmed any opposition. Faster than steel could be shaped in traditional methods, simpler than conventional engineering wisdom suggested possible, adequate in every way that mattered, and available wherever needed. Donald Bailey's simple rectangular panels, dismissed as garden fence engineering, carried the Allied armies to victory. American industrial might transform those panels from a clever British invention into a war-winning system. The bridge that was too simple to work properly ended up working better than anything designed by committee, refined by experts, or approved by conventional wisdom. The panels are still in use today, in modified forms, across the world. Every time a disaster strikes and emergency bridges appear within days, the design traces back to that envelope sketch in 1940. Every time military engineers need a bridge immediately, the solution still involves modular panels, pin connections, and the principle that adequate and fast beats perfect and slow. 1. Engineers' rejected blueprint didn't just build bridges. It built the road to victory, one simple steel panel at a time, assembled by ordinary soldiers who proved that in modern warfare, building matters as much as fighting. America learned that lesson, industrialized it, and turned it into millions of tons of steel panels that crossed every river between North Africa and Berlin. The bridges are gone now, dismantled and repurposed decades ago, but the principle remains. Sometimes the best solution is the simplest one. Sometimes rejected ideas contain more wisdom than approved consensus. And sometimes winning requires not engineering excellence but engineering adequacy, produced faster than anyone thought possible, by people who learned that good enough, done now, beats perfect, done eventually.